Welcome everyone to memflow Applied Episode 3, a series where we will be applying memflow to make a memory scanner. In this episode, we will actually go into memory scanning. But to recap, in the previous episode, we made quite a few memory optimizations to make it go many times faster. But yeah, in this episode, what we will be doing is creating a system that will scan all the heap for an arbitrary input and find matches in it, and then eliminate the matches by rescanning with different values. So without anything further to do, let's get started. So first of all, I will show you the structure of our new target program, which we will be coding against, and that will be this program. It's quite a bit of things happening, but basically I wanted to simulate a tree structure of various heap allocated objects. Basically, we have some global state right over here. It's behind a lock-in. It's a global variable, and it contains a state structure which has current tick and account, maybe like a bank account or something. And it's also in a box, which means it's heap allocated. And what's in account? In account, we have name, we have money, and we have access count. What we're interested in is money or access counts. We will see whichever is more interesting. And basically, this is originally initialized as none. And what we do is in our main function, we read username, just some random name, and then initialize the global state with a new account with starting with 100 something money. And then we go into loop, which is a typical loop like the previous one, where we print out the global state, then wait for the new line character to be read, and then just call a tick function, which basically increments the tick counter and then does some money operations. And just to show you, right here, we have our structs binary, which we open up. It asks for a name, Jeff Ori, and it prints this whole structure. And we can press enter, and as you can see, things are changing basically. If we hold down, like money is going down by 9 and then gets incremented by 11, and ticks are going up. And basically this is what we're going to be searching. We're gonna try finding the money value and changing it to something bigger, better, and so on. And one last thing, overflowing that like button. Come on guys, do it. My goal is to get to negative 2.1 billion likes, but that first involves going over 2.1 billion likes. See, overflow. You get me, and I need your help for that. Your like helps me tremendously. If I reach that goal, I'll be forever grateful for you guys. Even if I don't, I'm so grateful for you guys. Thank you very much. And what do we start with? First of all, what we're gonna do is not actually scan just the executable memory, because in bigger programs, you may have important memory on various different modules. And also, this is a global object that's heap allocated, so it won't be on the module memory. Instead, it will be on the heap. And where's the heap? That is a good question. But we actually don't know. What we will be doing instead is scanning entire memory of the program, which poses an interesting question. How are we gonna scan entire memory of it? Because on 64-bit machines, there's like 256 terabytes of memory. How do we scan that? Well, there's an interesting feature in memflow called pagemap, and pagemap basically returns memory regions which were mapped in the RAM. It's all we basically need. We need all those regions, we scan through the regions, and we're good. I'm actually gonna delete all these because we won't be using them anymore. And we don't need the base either. But what we need is the page map. And that will be process.virtualmemory.virt page map. Yeah, I think something like that. Let's see. We actually got it correctly. So we got the mem map. So what is this function? This function, virt page map, returns mapped regions, like I said. The argument is basically a size, which the function will check to merge regions, because usually there are like quite a few scattered memory pages around, and some pages are not mapped in, some pages are mapped in, and you end up like 100 gaps within 2 megabytes or something. And we could just merge it all into one thing. So that's exactly what we're gonna do. We're gonna type in size. Let's merge like 16 megabytes. And size is a memflow type for sizes. And basically all you have to do is just import it. Use memflow types size. And if we build it again, we're not using quite a few things, but and what we're gonna do is just print the memory map. For each entry in the memory map, we are just gonna print address and size. We didn't find the process because, of course, we are changing this to structs binary. We also need to change this one as well. Here we go. And what we have here are the memory mappings merged by 16 megabytes. And you can see they can be smaller than 16 megabytes, but like in the middle, it merges those gaps up to that size. And we first have quite a few lower range memory, and then there is the kernel side. We're actually interested only in the lower range. So what we're gonna do, we know that the virtual memory address space is 48 bits. We're gonna pass the range function, the size first, then 0.into, and then 1u64 47. Here we go. This should work. And here we go. We have a rather small memory range. So basically what we did here is extract the page map range from null address to 47 bits, which is the lower half of virtual address space for a modern computers, which we did simply because, well, we kind of only care about that lower half because our memory won't be in the kernel memory. That's not where the program memory resides, I got to say. So now we've got our page map, which we will actually move over to scanner. We're gonna create a scanner object, which will hold the state for our scans. It will allow us to easily call scan for this value, and then rescan for it, rescan for it, rescan for it, get all the matches, get right to that particular match, and like all that fun stuff. It will be put into the scanner instance, which will allow us to basically abstract it all away very, very nicely. It will be a value scanner. And it will be, we will create a structure, value scanner, and implementation of value scanner. By itself, it shouldn't get the memory, but it will have a list of matches, and it will be matches, so back address, and for storage, address is really cool because it has all these nice functions and it has like these restrictions that allow you to only do sane things, like adding two addresses together is not very sane, I'd say. It's really cool, I'd say. And what we're gonna have is a function which is gonna be, one function will be scan. It will be take a mutable self, will be scan for we're gonna scan for something. And the most versatile form of data is an array of bytes. So we're actually gonna scan for a byte slice. Return self, because it makes it easy to chain operations. And here we will actually be doing the scanning. One thing though, what we need is virtual memory. We need a virtual memory object, so it will be this particular type, and we will use memflow mem virtual memory and probably virtual read data. So it all runs because we're not importing it yet. So yeah. But we will actually be importing it. It will be mod value scanner and use value scanner. Here we go. We default the implementation to just empty values. And what we're gonna do is actually create a scanner. Here we go. We create a scanner instance with nothing, basically. We're also gonna have the mem map address usize. And basically, what we're gonna do is just do this. Create a memory map, and we just do self.memory map. And it will be this. Now nothing will happen because... Oh, process, yeah. We just need to use mem instead. Here we go. All right, now we don't do anything because we actually don't scan for anything. And what shall we scan for? Well, right here, we could scan for number 109, which is the money value. It will be scan for, we pass memory, right? And then 109 dot money. For some reason, I set money as an integer. All right, dead. So we just do I64. And we have an error, which is... All right. There we go. At this point, we actually scan for the value thing or whatever. And we have this. And we also have a matches iterator, which returns an iterator. There we go. We had a bit of a lifetime issue because we return an iterator of matches, but the iterator must not outlive the scanner. So yeah, we solved the lifetime issue, and now what we need to do is actually just scan for stuff, which we will do by... We also need to add a reset function. And the reset function is just gonna do return mutable self, and it's just gonna do matches of clear, self. All right, and now what we need to do is actually just scan the memory like we did in the previous episode. What we're gonna do is just go to the memflow applied repo and go to the source and find our memory scanner. It will be this one, which is the fastest scanner, obviously. And what we're gonna do is go through right here. If matches dot is empty, we do this. We create a memory map and stuff and scan for memory. Else, we will go to else probably in the next episode. But here we have the mem map. We're gonna go read page by page throughout the memory map and look for the matches. Look for the matches like we did in our previous episodes, and then add them to the matches list. And to do that, we currently have iterate through address size pairs. We're just gonna go and do for 0 to size. It will be called offset. And we step by one page. We do memory, and it will be address plus offset, and it will be buff as image slice, and we allow partial results, and buffer is let buffer equals spec 0, and it will be 0 to 1000 plus data.len -1. And what this is going to allow us to do is allow us to find data which crosses page boundaries very, very well. We perform these reads. Once the reads are done, we're just going to do we just create the windows of data.len, and we enumerate it all. Once it's all nicely enumerated, we're just gonna do the checks if buff equals data, and if data is equal, we just do match found at address plus of plus O, and we're just gonna do that right here. Yeah, result, and return okay self. Basically, we're doing this for import it all. Slice, we are doing typos. Do it over here. Here we go. We did it. We actually found the match. Atch. We found the atch. But yeah, we found an atch of, what was it? 109. We've got the match of 109 over here. And what we're just gonna do, instead of printing it out, we're just gonna do self.matches.push. Push address plus offset plus O. And here we go. We have it all very well made. And we're just gonna go and do matches found. And it will be value scanner dot matches iterator dot count. Actually, we're just gonna rename it to matches dot count. We run it. Matches found. We found 5 matches, which is really cool. And what we're gonna do, if we just press enter once, now it founds one less match, which it basically is our match is gone. Now we just need to check for 119 instead. 119. And we've got 4 matches of 119, which is pretty snazzy. If we have now 3 matches 119 because we decreased that to 118. Let me just show you real quick. Yeah, you can see it's 118 now. We just gonna do this. Now we've got 7 matches because like it finds other memory again. But yeah, what we basically did now, we moved this into a separate module which finds matches and saves them, and then we can actually print the matches. Let me actually print them. Do for in value scanner dot matches. Do and we have this all these matches, and if we just go here 115, recompile it to do 115, cargo run it, we've got quite a few matches this time around because it's probably some really interesting opcode. Here we go, we went back to something sane. And what is matching? Well, AB28 is matching. So that means that, well, this is our match. And what we're gonna do with the match, well, this is up to the next episode. But yeah, we actually did it. Let me just recap real quick what we did. We first of all removed all the old code. We created this value scanner structure, which holds matches in the memory map. And if it's all empty, it creates a memory map which allows us to know which memory regions to scan, because otherwise there would be a bazillion addresses to scan for. So once you've got the memory map, we're doing pretty much the same thing as in the last episode of the most efficient way of scanning things, which is basically creating a buffer which is just over 1 page of size and just reading data one by one. But instead we had another loop. We had another loop in addition. Instead of going through just one module, we're going through some number of address and size pairs which define a memory range. It could be this, it could be that, it could be whatever. And once you go through that, we find our matches, and instead of printing the matches out, we add them to the match list. And match list, basically, we are able to print out the match list by accessing them and counting them and also iterating through them. You print the matches and you've got the matches, which are numerous things, numerous matches we found, which is corresponding to our program. In the next episode, what we will be doing is we will be adding filtering and user input for scanning subsequent values to filter out all these unnecessary matches. As you saw in here, you've got quite a few matches, but if we are able to just increment this to like 115, we then are able to just enter in the console 115 and it will search for 115 and it will filter out all these static matches which don't change to 115. And basically this is the core of Cheat Engine. It scans for memory matches, then you enter additional match for when your memory has changed. And once it's changed, it filters them out. Once they're filtered out, you see a smaller list of probably what we're looking for. So yeah, this was it. Thank you guys for watching. And don't forget to like this video, subscribe, hit that bell icon, share it with your friends who would love DMA. And thank you for watching and bye-bye. Oh wait, my name was Heap. Yours was undefined. See ya.